And so, Anna,
Yes, congratulations on beginning your summer school. So I will give the second lecture on small x physics, and I'll start with a reminder what we learned yesterday. So we looked at, started from collinear paradigm of DIS, and we reminded ourselves what is collinear factorization and D-glab evolution, and it works very well. And then we learned that small x has quite a bit of history. It stems from the this S matrix, analytic S matrix, and this is where the Pomeron concept of the Pomeron was introduced. And then we learned how this Pomeron can be realized in QCD, and that is through what is called the cutting part of the FPL equation at small x, which is analog, which is sort of a counterpart to D-glab, except that it evolves in a different variable. And then we looked in some detail in beyond the leading log x, and I argued that one actually needs to go there, not even to next leading log, but to perform the resummation in order to stabilize the series. And then we also learned about the saturation. So on top of the resummation, there are other classes of effects, and Raju was talking about that. When you go to high density region, you need to actually take into account gluon merging, and this brings into the non-linearity. So the linear equation becomes non-linear, and there is a saturation scale which divides the dilute and dense regimes. I didn't get a chance to talk about the impact parameter dependence. I answer any questions if you have about it. The slides are there. Very interesting problem. So what I want to do today is to give you an overview, of course, a selected overview of some processes that you can look at, mostly at DIS, but also at other machines, to actually look for small x phenomena, either BFKL or saturation. And I will start with actually looking at hints in structure functions data at Hera that actually the BFKL evolution might be necessary there. And I will discuss how to possibly look at small x and saturation effects in the context of inclusive structure functions. And there, in fact, the FL structure function is quite important. I will go over and briefly discuss also two-scale, what is called the two-scale processes, which you can look at both DIS, but also at other machines like LHC, but also in E plus E minus collider. So I will show some processes that you can search for small x physics there. I will also talk about angular correlations, how you can use correlations of or decorrelations of hadrons or jets to search for small x effects. And I will also spend some time, well, quite a large time on diffraction. So this is sort of this evolution plane, and Raju actually was talking about the same plane, but he flipped the axis. So his x-axis was here and Q's were here. So everybody has some favorite way of presenting the same plot, but the content is the following, right? So we have the D-glab evolution with increasing scale here, and then the BFKL operates in this direction here. And once you go to sufficiently high energies of small x, you're entering this dense region that is divided from the dilute region by the saturation scale, that it's x dependent, right? So essentially it's a straight line. And this power is from theory about 0.3, but it varies. Now, theory cannot really predict what is the normalization. So where this where this line is, and this has to be really taken from, well, fixed by an experiment. Now, this saturation scale is enhanced, so there's a factor, roughly speaking, I mean, this is sort of a simplified formula, of course, but is enhanced by nuclei. So if you have a large nucleus, the saturation scale is larger, and so you might have expect stronger effects there. So if you fix Q, so in some sense, this plot has another dimension. If you fix Q, you can sort of look into log A and log 1 over X. And then you can, if this is the dilute region between large X and small a, you can, so the idea is that you can enter this dense region going either through EP collisions or some PP, some other collisions, but very, very small X, or maybe if the X is moderate, by going into heavier nuclei. So this gives opportunity at the IC, particularly in the context of physics with nuclei, to test these ideas of saturation. Okay, so EIC, you know, that what are the capabilities? It has beams from different A, from light to heavy nuclei. It has polarized electron and nucleon beams and possibility of polarized ion, and variable center of mass energies. That is very important, from 20 to 140 GeV, as well as very high luminosity. So we can look at rare processes. So in the context of, for example, physics with nuclei, this is the range of the EIC kinematics. This is some example of a saturation scale for gold. And so you can see how you can probe this this region with the AIC. And then in EP, this is the AIC kinematics with EP. Together is some data. These are actually polarized data. So it sort of covers axis down to maybe 10 to minus 4 at Q squared equal to 1, sort of small to moderate axis. Okay, so what we can learn at EIC, I give you here sort of the list, and I will talk about these things. First of all, it can measure nuclear structure functions, and it can test the limits of collinear factorization. And therefore, it can also test the onset of saturation in years. So test whether DGLAB works or whether DGLAB fails, and whether we would need some nonlinear corrections. It also has possibility of measuring precisely FL, proton and nuclei. And then there's a whole program of diffraction where one can measure diffractive nuclear PDFs, which would be possible for the first time. And there is a close relation, as I will tell you, between diffraction and small x physics. It can measure diffractive to inclusive ratios, which are very sensitive to different scenarios. For example, saturation physics versus other scenarios, and exclusive diffraction, which is, for example, the exclusive diffraction of vector mesons, which is excellent process for mapping the spatial distribution and also test saturation. Okay, so going back into the inclusive processes, right? Structure functions, we've seen this plot yesterday. These are Hera data as a function of Q squared for different x's. This is reduced cross-section, combined measurements, excellent description with DGLAB. So the question is, can one look at inclusive structure functions, and are there any small x effects visible in these inclusive structure functions? So there has been several approaches, and so in this calculation, what has been done, they compared fixed order DGLAB to DGLAB supplemented with a small x resummation. Something that I outlined before in a slightly different framework, but essentially the basic ingredients are the same. And what was done was to take all the Hera data, X and Q square, and then perform the fits at next to next leading log, next to leading log, and then next to leading log with the resummation, next to leading log with resummation, and then systematically cut out data at small x and small q square and see the stability in chi-square. And this is the result. So here, the smaller this d value is, the more data are cut. So here there are more data cut, and here more data are included. And so we see that there is a variation in chi-square at the fixed for next to leading order DGLAB as you include more and more small x data. Okay, so something is going on here. Whereas if you include the resummation, this becomes this blue, it stabilizes. Okay. Now, so it gives a hint that maybe there is something beyond DGLAB that is going on here. Interestingly, although, the next leading order is not as, so if you perform the analysis at the order which is less, actually you don't see this sensitivity. That may be probably explained by the fact the peculiar behavior of the splitting function. If you look at the splitting function, at fixed next to leading order is actually flat, and the resummed is almost flat. So whereas at next to leading log, it has some behavior with x. So this gives us some idea that resummation of small x effects might be already entering for the description. It might be necessary for the description of the Hera data. Now, it becomes more evident here when they looked at FL. So this is a FL structure function. And then you have a fixed order. So here are data, and you have a fixed order description, the green bars, and then these magenta are the results. So essentially putting in the small x effects improved the description of the longitudinal structure function. Yeah.
Where is NLO on this? Where would NLO be?
Yes, I mean, I don't have a plot with NLO, but I think it was not too bad in terms of describing the data. So essentially, you know, once you go, it's again the same. The next to leading log is slightly worse than the next to leading log. Now, if you had a machine that would go to extremely small x, then you would expect that these effects are amplified. Now, so here are predictions. You basically take the calculations, extrapolate them to much smaller values of x, which is 10 to minus 6. This type of range would be could be accessible at other machines, and there are proposals to build such machines at CERN and essentially supplement the LHC protons with electrons, the deep inelastic scattering at the TeV range. That would allow you to push to really small x. So there are some dots, points here. So these are the simulated pseudo data, and then you see the prediction in blue, which is this next leading log, this resummed calculation, and then this hashed region. This is the fixed order calculation. So you start to see the divergence, but it's still, I mean, you have to go to 10 to minus 6. However, if you go to FL, it seems that the differences are much larger, right? So they, even at 10 to minus 3 to 10 to minus 4, you start to see the deviation, okay? And this is important because this is essentially the region, like I showed you in the kinematic plot, that can be accessed by EIC. So if IC has very, very precise measurement of FL, this is really going to be sensitive to effects like that. Okay, so EIC, because it's in lower energy, it's not going to go here, but it's going to sit somewhere here. Still, if you have a very high precision, thanks to high luminosity and varying energies, you can probably pin down this and say something about the difference. Okay, so now these predictions that I showed you were without saturation. Then you can also add on saturation and ask for whether or not these nonlinear effects and how they are going to be how they will manifest themselves in the structure function. So this is a study done for nuclei, and the study went the following. So what was done was essentially calculation with DGLUP and then calculation with BK. And then the idea was to match these calculations. These calculations were matched at the particular values of X and Q squared, okay? And then the question was asked, well, when you evolve away from this region, well, how do they differ, okay? And so you basically take the difference like that. So this is a DGLUP calculation. This is nonlinear divided by nonlinear. And then you see sort of in colors where the difference is positive in red and negative in blue. Okay, so you can kind of see visually where they are different. And the stronger the color, the bigger the difference. Okay, so this is again F2 and FL, right? And you see that for FL, these differences are bigger. So for the heavy nucleus, the difference between DGLUP and nonlinear are maybe a few percent for F2. So that is quite small. However, they're up to 20% for FL. Okay, so this is that would provide you a sensitivity to these effects, because in these inclusive measurements, when you want to say, okay, is saturation working nonlinear, or is DGLUP working, and where DGLUP stops working, that the problem is always you have some initial conditions that you can adjust. And there is quite a bit of flexibility in these initial conditions. So it is really important to have another observable so that you can essentially make have better constraint. So now it is difficult measurement in FL. So this is just as a reminder, the inclusive cross section in terms of F2, F and FL, right? And you can write the reduced cross section like that. So when you measure the cross section, you essentially measure this combination at fixed X and Q square. But then when you want to extract FL or F2 separately, what you need a variation of this factor, which depends on inelasticity. Okay, so then if you fix X and Q square, you actually need to have different energies, right? So then what happens is you can plot this function as a function of this variable, right, for fixed X and Q square, and then you can extract sort of the intercept that would give you F2 and the slope would give you FL. Okay, this is how it was done at Hera. So you need varying energies, right? So, but this is possible at EIC because EIC has this. Yeah.
Do we ever move out of the DIS regime? So for very small y or very large y, we're always still in deep inelastic scattering, no matter how small it goes.
What do you mean we are outside DIS regime?
Because like for y, the variable defined this way or defined as like the loss in lepton energy.
Sure.
That. But is it, if you lose a teeny tiny amount of energy, do you ever just say, okay, that actually wasn't inelastic, that was just inelastic? Or are we always in the DIS regime?
Well, I mean, you have, so then if you're, okay, so of course these variables are correlated. I mean, at some point you go to the production regime, right? So you're not really, your Q square is not large, right? So I mean, for me, the deep inelastic scattering is sort of, well, it depends what you mean, right? I mean, it's a process itself like that, right? Okay, so this was about the inclusive structure functions. Now I want to move to something else and talk, switch gears and talk not only about the deep inelastic electron nucleon, but also some other processes, like, for example, you can test it at proton-proton collider. So the idea here is that, like, we had this diagram where you have essentially some cascade of these strongly ordered in longitudinal momenta partons that are being emitted. And you have two scales, and you want these scales to be perturbative. And the idea is that what BFGAL does, it essentially allows you the random, so there will be a random walk in these transverse momenta. Okay. So, so you can look at two things here. What would be this BFGAL signal? First of all, it would be as you increase this distance, the cross section would grow rapidly, because that's the nature of BFGAL. And also what you can look is, if you can look, for example, into the jets, like here and here, there's some jet being produced, then you can look at how they are correlated or decorrelated. Okay, and depending on the parton dynamics here, this will influence the correlation. Okay, so this principle can be applied to very different machines. So you can look at DIS and you can ask for a forward jet. So the jet is in the forward proton direction. And you have a large scale here of your photon, and you want to have comparable scale of your forward jet. And then you have this BFGAL cascade in between. Or you can go into E plus, E minus, if you have enough energy, and look at so-called double tagged events where electrons are scattered at some angle. So here you have a photon, here you have a photon, and here you have cascade of gluons. Okay? Again, the same similar process. Or you could look for jets in PP. For example, here you ask for a jet, here another jet, similar similar transverse energies, and then you have a cascade in between. Okay. So I will show you what are the results for these three in three different machines. So the forward jets, you can ask for forward jet in DIS or a forward particle. So this is gamma star P plus, and you ask for a jet and then the rest. And this XJ, so this XJ, sorry, this is XJP, so there should be P here. Okay, so this is the longitudinal momentum fraction of the proton carried by this jet. Okay, and you want this to be much larger than X, or this log to be large, because you want to have this rapidity distance here large. Okay? And you want to have, to suppress the D-glab evolution, you want to have Q square comparable. So you want to have this jet hard enough comparable with Q square. Okay? If you can look also for some forward particle, for example, I0, right? So you think of this, there is some parton and then it fragments and then there are some particles. So depending on the setup of your detector, what you can measure. So it could be pi0 or some charged particle. Okay, but the principle is the same. So these are the data from HERA, something similar you can do at the AC. So here you see the data as a function of X. Forgot to specify what was the PT of the jet here, but you can look it up. Now the cross section does increase steeply towards the small x, and you see that most of the Monte Carlos basically sit below. Okay? There's only one Monte Carlo, this Ariadne, that kind of catches up to the data, and it has some dynamics that has is similar to BFKL. On this plot, you see what you see. You see the histogram where you have an ET square of a jet over Q square. So essentially, this region here, when this variable is small, is kind of a region where you would, so the small PT of the jet and the large Q square, you would expect that the DGLAB physics is correct. And indeed, you kind of see that these Monte Carlos are tracing these points. And then the DGLAB sort of base Monte Carlos, which are these dashed lines, they kind of start to fall below. Ariadne is maybe better, but then here it starts to be too high. So I would say neither of them describes the data perfectly, but certainly you can say that something is missing there. So maybe there is a physics, small x physics there. Similarly, this is the forward pi 0, the data from HERA. Different values of Q square, and you go to smaller and smaller x. So the smaller Q square, you can of course go to smaller x. And you see this dash dotted line is actually describing the data. Well, it's consistent, a little bit overshooting the data. There is another line that does describe the data. This is called the direct and resolved photon, which kind of sounds the same. It sounds different in a sense that it includes what is called the resolved photon structure, some cascade from the structure on the photon side. But if you kind of look into the details, it can be interpreted as part of the BFKL framework. So I would say that there are some suggestions that this dynamics is present there at HERA if you look at these processes. Okay, so now moving briefly outside the DIS machines to E plus E minus. You can measure, you can test small x physics in E plus E minus, and that has been done. So you look at two electrons, electron and positron, and they are scattering. You have a double tagged event. So there are three classes. Okay, so anti-tagged or no tag. So then basically you don't see the electrons because the unit scatters. So Q squares are small. So that's one possibility. Then you can have a single tag when you measure one electron. So Q2 squared should be bigger than Q1 squared, which is approximately the root 0. And then double tagged, when you tag two electrons, it means that both of these are large. And then this is very nice process because this is, again, this process where you have two perturbative scales comparable, and then you have this emission. Okay? And you see this is tractable in BFKL and has actually been measured at lab. Now, what are the contributions, other contributions? So at fixed order, you have photon into quarks or quarks with some gluons or gluon emissions. So you have these, but these do not give the energy rise. So these would basically fall down with energy. And then you have sort of the BFKL-like. So this is sort of the Born diagram where you have one single exchange and then single exchange with gluon emissions. This is precisely the BFKL ladder. Okay, so this one would give you a constant energy, and this one would give you increasing energy. Okay, so this process is enhanced. Now we have recently calculated this process using resummation. I don't want to go to details of that, but we put the gluon-Green's function, which was resummed, something that we talked yesterday, but also impact factors that we need to resum. So this is a full calculation, and we computed this cross section and compared it with the data. So this is kind of warm result from the oven, if you wish. So here you have data. This is for L3. They have slightly different Q scores, so this is why I'm I'm plotting the Q square of the both photons. And here you have different scenarios for the resummation. Okay, and then this line is essentially the quark box. Okay, so the photon, this diagram here. Okay, so you see that it goes down with the energy. And if you include BFL, you kind of get this flattish behavior. Now, the data are what they are, but with large error bars, but it consistently seems that they are flat or even rising, and they are consistent with this resummation. So maybe even in lab, we are starting to see this type of BFL dynamics. Okay. Similarly, now at LHC, we have much higher energy. We can measure similar processes. And there we can look at jets. So you have a proton coming in, and then you ask for two jets. And then they are separated by large rapidity interval, and then you look for this radiation. So in this plane, you have a proton coming in, you have two jets. And what you can do is also look at how they are correlated in this angle. So there will be some angle of this jet 1, jet 2, and whether they are back to back or how far from being back to back they are. Okay, so this gives you an opportunity to test the BFL evolution at the LHC. One of many possibilities, but this is one example. So, for example, one can look at these correlations and take this cross section. So this is differential cross section in rapidities, in transverse momenta, and in angles, and you decompose it into these Fourier coefficients, CNs. And this is very sensitive to parton dynamics, right? So if two hard jets, if there are only two hard jets in the final state, you would expect them to be approximately back-to-back in azimuthal plane. But because you have a parton radiation, then this parton radiation will lead to this angular distribution, which will have non-zero width, okay? And then the shape of this angular distribution then is determined by these coefficients, right? So now you're going into very large, very small details. You can learn a lot if you study these angular coefficients, right? Because it's kind of, one thing is to describe the very inclusive cross sections, but if one can describe these coefficients, that gives you quite a bit of information about the dynamics. And in BFL, one does expect a lot of these decorrelations because of these unordered cascades and with increasing rapidity. And then in DGLAB, because of the strong ordering, that implies that this will not affect jet correlation as much. So there will be some difference. So these are the results, and they are confusing, to say the least. I was studying this paper and CMS paper, and I must say it's very confusing in terms of the final conclusions. So here, these are ratios of these Fourier coefficients as a function of rapidity, C2 over C1 and C3 over C2. And then left and right are just different Monte Carlo and different calculations overlaid. Now, the BFL is, I think this is the BFL calculation, and it kind of, is okay-ish with the data, although here I would say it's maybe too large. And also, this particular calculation doesn't show what's happening here. Monte Carlo are all over the place, although I would say that there are a bunch of Monte Carlos that for lower rapidity differences work very well. It is this high rapidity difference, precisely this region, where they start to have problems. Okay. Now, it seems that the color coherence plays some role. Some Monte Carlos do better than the others, but clearly there is a different dynamics here because they all struggle to get a consistent description. Yeah. Yeah, so this is essentially color coherence is a property where you have emissions that are angularly ordered along the cascade. Okay, and so that is implemented in some of these Monte Carlos, and it seems to, well, that that is important. On the other hand, the multi-parton interactions, surprisingly, actually do not play the role here in these calculations. So I would say that the verdict is still, I think it's an open question. I would say that we need probably more theory and experimental studies to say that this is really a signature, strong signature of the physics. Okay, now, while we are at these decorrelations, we can also study these type of decorrelations at the EIC in a slightly different setup. So instead of looking at the correlations of two jets which are separated by rapidity, you can also say, okay, let me look at the correlations of two jets that are very close in rapidity, but then there is some chain sort of attached. So you look at these two jets which are here produced here, and then there is some rapidity difference to the proton side. So again, there will be a signal in this angular distribution depending on what happens here. So how many emissions you have, what type of dynamics you have, do you have saturation or not? So this can be looked at the EIC and both in EP and EA. And you would expect if you have more saturation, so more multiple scattering here, then there will be more decorrelation of these partons. Okay, so you can look at these two hadrons or two jets. So you can look at this correlation function. And this is the prediction for the EIC this time. So as a function of the angle. And then this is for EP and this is for EA. Okay, so you see that you have these dihadrons are becoming more decorrelated when you have scattering on the nucleus, and that is attributed to the fact that you have more saturation because you have more essentially multiple scatterings. There is higher saturation scale. The suppression and the width of this distribution is going to reflect the parton dynamics and in particular the saturation scale. So this principle can be applied, so dihadron, dijets, but also in diffraction and in photon plus jets or dijets. So there is a plethora of processes they can, this principle can be applied at the EIC. Yeah.
But why are we calling them dihadrons? I thought they were dipartons.
So yeah, so here, well, so of course we calculate partons here, and then the question is what do you look at? You can look at jets, right? Or you can look at hadrons, right? And that depends on which, well, ideally you would like to measure both, but you know, it may be preferable to measure other depending on the type of detectors one has, right? And kinematics, right? I mean, you need to call something a jet, you really need a well-defined jet. So then you enter into this, into these questions. Maybe it's better to measure hadrons. Then, of course, you have to deal with fragmentation functions, right? So, you know, there are pros and cons of doing this, but of course, we can only calculate on the level of partons. So the rest of my time I want to spend on diffraction in deep inelastic scattering, because this is also a process that is closely related to the saturation and low X dynamics. And there you are looking at, so you're looking at your inclined photon, and then this is your proton, and then here, this is the exchange of this pomeron, and then here you have no radiation. So the definition of the diffractive event is that you're looking at an event where at some point there is a large rapidity gap with no activity in the detector. And for this to happen, you need some colorless exchange, because if you exchange color, then you start radiating. Now, this diffractive process, in addition to the standard variables, there are diffractive variables, Xi or X power beta and T. So this Xi and beta, when you multiply, this gives you X, because these are just momentum fractions. So this Xi is a momentum fraction of whatever this exchange with respect to the hadron. And then beta is the momentum fraction with respect to this and you have a momentum transfer. Okay. Now it can also you can have a dissociative case where the proton dissociates into some state with the same quantum numbers, but there is still a rapidity gap. Then we are talking about dissociative diffraction. Okay, so so this was a non-diffractive event cartoon that I showed yesterday. So you have a proton and a lepton, and then here everything is populated. Now here you have an example of a diffractive event. This time the electron goes sort of, is not very, it's not a very large angle scattering, but there is a gap. So the proton escapes here more or less, but there's a gap here. Okay, you don't see any activity in the detector. And about 10% of events at Hera were of diffractive type. So it's a large fraction. This is a very curious event, right? Because if you think about, you know, from the perspective of the rest frame of a proton, you hit it with extremely high energy and it stays intact. Okay. So this is the diffractive kinematics for Hera and 3 EIC scenarios in X and Q square, and these are the diffractive data. So EIC would have a very large overlap with Hera and then potentially also go to larger values. So this would be also studying interesting physics connected to the region exchanges. Now, why this is interesting to look at diffraction is because you have, first of all, you need this color singlet here. So, and this, if this proton stays intact, then you have automatically there must be some relation to confinement, right? Now, it's also very sensitive to, it's dominated by gluons. And so it's very sensitive to gluons and low X dynamics and saturation. There are connections there. It's related to nuclear shadowing. And you can test also the limits of factorization and universality of diffractive PDFs. And for some processes, you can learn about the spatial distribution of the gluons in the target if you have the information about this momentum transfer dependence. Now, in nuclei, there is also what is possible is incoherent diffraction. Nucleus is very easy to break up if you kick it hard enough. So you can have this rapidity gap, but the nucleus breaks up into parts. And of course, on protons, you can break it up. So this is called the diffractive dissociation. Okay. Now, similarly, you can measure structure functions in diffraction. So the cross-section, diffractive cross-section is written in a very similar way, but now it depends on 4 variables instead of 2. Okay. So in C, beta, Q square, and T. Or you can actually integrate over T, and then it depends on 3 variables. There is also F2 and FL, so it's just same thing. And here you have an example of pseudo data for diffraction at electron proton collider. And in fact, we had to rescale these error bars by a factor of 2 to make them visible. So you see the very, very precise measurement that you can have at EIC for these diffractive structure function. And then you can also extract diffractive parton distributions and perform the evolution and all the things that with diffraction. Now, what is also possible at EIC is to, and I argued that for inclusive FL, it is also possible to measure FL in diffraction, which is going to be, so this quantity here, this quantity vanishes in the parton model, but gets non-vanishing contribution in QCD. And as in inclusive case, it is also very sensitive to gluon dynamics. So it is another very important observable that will help us to provide information about saturation and nonlinear phenomena. This is a very difficult measurement. It was performed by H1 because it requires several beam energies. This FL is strongest when this Y is 1, so low electron energies. There were only 4 energies at H1. There were large errors which were limited by statistics, which is not going to be the case at EIC because we are not going to be limited by statistics. We have done some simulations on that, and this is what you can extract. So for if you have 5 energies, 9 energies, 17 energies, different colors represent here different Monte Carlo replicas. So it is possible to, one has to be careful which energies to choose, but it is possible to measure the FLD diffractive at the EIC, and it would be really nice to do so because it would provide a lot of information. Now, one thing that you can also measure at the EIC is inclusive diffraction on nuclei. So you look at inclusive structure function in the problem, inclusive structure function in the nucleus. And here what I show is 2 models. So there is one model, this is calcium, this is lead, and this is this is U and the gluon. What you observe, and then these are 2 different models. What you observe is that these curves are all below 1. So this calculation, called the leading twist shadowing calculation, predicts suppression of the diffractive structure function for nucleus over the proton. That's what it says. On the other hand, in saturation, you see that, okay, except for calcium, well, calcium goes here about 1, but for heavier nuclei, you expect enhancement. It's a very different prediction, dramatically different, right? I mean, the ratio in one case is above 1, in the other case is below 1. So this is a very, I think, interesting and important measurement to be done at EIC, measuring diffraction, simple diffraction on nuclei and on protons, two-dimensional, and see how saturation or the other models are doing, right? It's a very, right? Is below 1 or above 1. Okay, so this is quite striking. We don't really understand diffraction very well. Now, the final thing that I want to discuss is elastic vector meson production in EP and EA. So this is inclusive diffraction, but then you can kind of ask for different things to be produced here. Right? Either ask inclusively for a rapidity gap here and anything being produced, but you can also ask for, let's say there is just a vector meson being produced, like a J psi. Okay, so the final state is a lepton vector meson and the proton here. Okay, you can ask for J psi or epsilon. Now, this has been measured at HERA as well as a function of T, okay, for these regions of energy for photoproduction. And well, here is just an exponential fit, but if you have, if you can go further in T, you can map this dependence more in more detail. And the important information is that the T dependence of here provides you the information about the profile of this target, the transverse profile. Okay, so this is very similar to what you have in diffraction in optics. Okay, if you have a diffraction on a circular aperture, you see this diffractive pattern. If you have a rectangular aperture, you have something like that. And so if you look at your diffraction pattern, is essentially like a Fourier transform of the aperture field. And it tells you the structure of what is happening at the obstacle. And you can be more fancy, right? I mean, we all know this this famous picture, which is the Gosling-Franklin picture, right? This is a diffraction of the DNA. And by looking at the structure of this diffractive pattern, so where are these bars here? What is the angle between these two lines? You can learn a lot about the structure of the double helix, right? Because it's so diffraction can provide very detailed information about the structure of an object. Of course, you cannot destroy the object in the process, otherwise you don't have lasting diffraction. And so you kind of do a similar thing if you do this elastic vector meson production. It's kind of a very simple probe of what is going on here, and this target stays intact. And then you look at the scattering, how this proton scatters as a function of T. And you can extract, for example, the profile and the radius. So, for example, what is measured in diffractive vector meson production is actually different from the proton charge radius, right? So the proton charge radius is this value, and then this is about 0.5, 0.6. So it seems like these gluons are kind of more localized in a smaller region than quarks. Now,
Excuse me.
yes.
On the last slide, it looked like not only does the size differ, but there's also like an offset where the gluons are centered.
No, so this is just the way I pictured it. We don't know how it really looks like, right? Whether they are offset, whether they are, because there could be more than one such thing, right? There could be different spots or hotspots. Okay, yeah. So this is my imagination. But what you can do is you can also do it at different energies. So this is the same Q square, but it's a different energy. Okay, and then you can look at the slope, how it varies with the energy, and then you can extract. It kind of is increasing, seems to be increasing slowly with the energy. So you have expansion of this region with the energy. Now, what the EIC can do, now EIC can certainly measure this process with a very high precision, and also to a higher T, because it has more statistics and better detectors. So it can measure this to higher T, which gives you a more handle onto the shape of this function if you Fourier transform. So now you take essentially this, and roughly speaking, Fourier transform it to get the profile distribution like so. Okay, so this will tell you about the clone distribution in from this process. Okay, and then here you can see it how you can vary it with different values of x. So as you go to smaller and smaller x, this shape will change. Okay. And finally, you can do the same thing with nuclei. And here you can, so what happens is that this, so now this scale changed. This is a nucleus, so this is very small t, and then you start seeing dips in this distribution. And again, by taking into account this this curve, you can Fourier transform and obtain a profile in impact parameter. Now, if you do the saturation or no saturation calculation, that's the difference. So that's the difference between blue and open rectangles. So there is some difference here. It would be nice to measure it, although I don't know if there's enough experimental precision that can distinguish details like that. Now, there is, on top of that, there is another process, which is the incoherent production. These are these lines. So in nuclei, it would be very important to distinguish between the incoherent, which kind of swamps, basically dominates for large T, the coherent one, which only dominates at very small t. So this is really the experimental challenge to distinguish between this one and this one, right? So I remind you, so the coherent one is when you have the nucleus, J psi, and electron, and the incoherent one is when the nucleus breaks up, okay? And this incoherent, it also provides some information. And in fact, it can be shown that sort of provides the information about the fluctuations or the more details about the structure or the lumpiness of the source. So I think that's all. I'm almost on time. So in terms of physical small x with nuclei, I didn't talk a lot about the nuclear structure functions. You can measure a lot here, and then of course do the test of collinear factorization in nuclei. And then you can test whether the collinear factorization and DGLAB works for various nuclei, and or whether perhaps the nonlinear evolution is a better framework and explore concepts of saturation in Yale. So you can test the DGLAB versus nonlinear evolution as a function of X, A, and Q square very nicely. In my opinion, the FL is needed to make more robust sort of probably to have a better handle on this difference. And the other thing is the diffraction. So as far as the inclusive diffraction, there are lots of possibilities, especially for in the case of nuclear diffraction. This diffractive to inclusive ratio of structure functions is, I think, very interesting, and because that there are strikingly different predictions, so it would be nice to measure it. And then there is the last part that I talked about was the exclusive diffraction of vector mesons, where it is an excellent process to map the spatial distribution of gluons in particular and test saturation ideas. So with that, I will conclude and be happy to take any questions.
Okay, we have time for questions. If folks have a few.
Could you please explain again how the dips in the coherent cross-section come?
Yes, so
They're connected to some excitations of the nucleus?
no, so the dips are okay. So essentially what you have is the following, right? I mean, if you have, so you could have dips also in on the proton, but they would probably appear very far in T. So now, so if you have essentially some profile in impact parameter, and let's say this is also related to the unitarity. But let's say you have a profile in impact parameter. Let's say this is some Gaussian distribution, right? Now you do the Fourier transform of that, Okay, if this is just a Gaussian in D, then what you will have is in T, you will have this exponential, right? Because the T is square root of T is related to is the Fourier transform of Fourier variable conjugated to T, okay? So if this is a logarithmic scale, then you get this ET, something like that. But if you have a nucleus is not like that. A nucleus, it looks like it's a Wood-Saxon distribution, more or less. So it's going to be like that. So it starts to become flat here. Okay. So if you do the Fourier transform of this, it's not going to be an exponential. It starts to have dips. So it basically goes, you know, like that. Right, something like that. For now, this is actually also related to the entirety question, because if you have something like that on a proton and you increase the energy, right, this shape will not stay Gaussian like that, but it's going to be modified, and at some point it's going to flatten and maybe have a shape like that. So what you would expect, for example, what you do in proton-proton elastic. So in the proton-proton elastic, you can extract the profile function in B, and you see that as you increase the energies, it kind of starts to, you know, do something like that. So it's becoming flatter and flatter. And this is related to the proton-proton elastic cross-section. If you look at the T, what is called the shrinkage of the diffractive T. Indeed, the dips in T in the elastic proton, actually they have, you know, dips like that, and then they kind of move towards smaller and smaller T. So so the dips are related to what is happening in here. But in so if you know, the more, so this size, if you have something that is like, if you were to do the Fourier transform of the beta function, then you get dips like that. The further out you go here, the smaller T the dip starts. Okay, so so yeah, so this is I think very interesting phenomenon with dips in both in nuclei and in proton. Yeah.
Connect this question mathematically. These dips come out as a zeros of Bessel function.
Yeah. Yeah, this is like, right, you do the Fourier transforms.
Do you think that we are going to be able to resolve this coherent structure in ultra-peripheral collisions, let's say at the LHC? Because that's what people already are measuring in ultra-peripheral heavy ion collisions. But I'm not sure what are the limitations of this approach compared, let's say, to what we are going to do at the
Yeah, so very good. So at UPCs, right, you can actually go to higher energies at LHC.
Yeah, that's
So this is one of the advantages. I think it's what you can do at EIC. You can well, one thing is that you can look at different nuclei, right? So that is really nice that you can see this shape as varying with the different value of A. Now, I think that last time I heard Kong too give a talk and thinking about how many dips he can uncover. He claims that maybe up to 3, but I mean this thing changes, right? It's I think work in progress by experimentalists as how many dips one can cover. Maybe one will be able to uncover only, you know, some changes like a derivative, but yeah, I mean, I think Kong is the expert there to ask about how many dips you can can see at the EIC.
He's actually my supervisor, so I can ask him.
Yes, so you can ask him, right?
I have a question related to that
Yeah.
one. We actually discussed this at recitation last night, but I want to get your perspective on it too. We learned last week that the EIC is not going to get down to as low values of X as Hera was able to. And if I'm not mistaken, Hera did not find any evidence of gluon saturation. So,
Yeah, I mean, so this is, so what I try to argue there is, so what seems to be the case is that there is some dynamics at Hera, which is at least in the, in inclusive case, certainly there is something going on at small x, but this can be described by the linear small x evolution. Now, in the context of diffraction, there was a measurement by Hera, which was also very striking, where the diffractive to inclusive ratio was measured, and it was flat as a function of the energy. Okay, and if you apply the saturation model would give you exactly.
oh, okay.
So for example, this was this Goles, Biernat, and Wüsthof model where they looked at this and did the prediction and compared with Hera data. I don't have a plot here, but what they showed is that this ratio was actually flat in some kinematic region. So that I wouldn't say that it was an evidence, but it was, it was at least not excluding the saturation completely.
Okay.
But I wouldn't say that the saturation was, when they also fitted the data at Hera with saturation, and then at Hera, the saturation scale comes out to be about 1 G, maybe at 10 to minus 4. So then you're in sort of this gray regime, or is it really perturbative QCD or not? Okay. Now, at EIC, you're right. I mean, we are at the higher X, so it's not as high energy. On the other hand, there is the possibility of going to nuclei, right?
Yes.
So this is where I think one can look at the deviation from the linear evolution, like, for example, in this analysis, or analysis of this kind, where you have inclusive structure functions and you have F2 and preferably FL, different values of A, right? And you do the DGLAB analysis, right? And you see how well you describe them given the precision of the data. Right now, of course, one describes the nuclear, the structure functions in nuclei with DGLAB very well. But maybe if the precision goes down to very, the error bars are much smaller, and you have FL, maybe you will start to see some differences where DGLAB will not be able to fit as well as, for example, the nonlinear approaches. So I would say that, ideally you would like to have a machine that you would go even to smaller values of X, but at EIC we have nuclei. So this is where I think one can test these ideas of saturation.
Okay.
Yeah.
All right.
More questions?
Okay, let's thank Anna again. Let me just a couple announcements before we oops, switch this.